Hi all, today we're going to talk about topic 4, quantitative changes in equilibrium systems. This will be a multi-part lesson where today we're going to be focusing on the reaction quotient. So we're going to try to define and derive it. We're going to explain its relationship to the equilibrium constant K. We're going to see how we can use it to predict which direction an equilibrium will shift. A system will shift to establish equilibrium, and we'll also perform some calculations with it. The last bullet point here, where we're going to use ice tables, reaction quotients, and equilibrium concentrations, we'll cover in another lesson. So we've spent a lot of time learning about equilibrium, trying to understand what the equilibrium law is and equilibrium constant, and these all involved using the concentration of reactants and products once an equilibrium has been established. However, it's not always going to be at equilibrium. So this gives us the question of what if the system is not at equilibrium? Okay, and that's where we're going to be coming and using the reaction quotient, Q, which will allow us to establish and investigate reactions that are not at equilibrium. And we're going to see that the reaction quotient is identical to your equilibrium constant. Okay, but instead of using equilibrium concentrations to plug into it, we're going to be using instantaneous concentrations at any time point during the reaction profile. Okay, where instantaneous concentrations are a set of concentration that correspond to a specific instant in time. So Q can determine if a system is at equilibrium. And if it's not at equilibrium, we're going to see how we can use it to predict which way an equilibrium will shift. Now, the reaction quotient, just like our equilibrium constant, is the product of the concentration of our products divided by the product of our concentration of our reactants. But the only difference is we're not dealing with equilibrium concentrations. So let's say we have this general equation. Our reaction quotient will be our products over our reactants raised to some power, which is going to be the coefficients in our balanced equations. Okay, and these will be identical. This is identical to what we did for the equilibrium constant. The only thing that's different is that it's not equilibrium concentrations that are necessarily plugged in. It can be concentrations at any point in time during the reaction. Similar to the equilibrium constant, there are no units for the reaction quotient. Now, the relationship between Q and K. So to predict the direction in which a chemical equilibrium will shift, we really just need to compare our values for Q and K. Okay, and it's the relative sizes between them that's going to dictate what's going to happen. And this really gives us 3 possible predictions. If Q is less than K, the ratio of products to reactants is smaller than when the chemical system is at equilibrium. So to move Q to K, the products must increase and the reactants must decrease. So the system must shift to the right. If Q is equal to K, the system is at equilibrium. No shift is going to occur. If Q is greater than K, the ratio of products to reactants is larger than when the chemical system is at equilibrium. To move Q to K, the products must decrease while the reactants must increase. So this chemical equilibrium must shift to the left. Okay. A nice way that I like to try to remember it is if we always set the orientation of Q to K like this, and we see that it's a less than sign, you can see that it's bigger over here, so it's going to shift in this direction. If we look at this one over here, you can see that the bigger part is on this side, so it's going to shift towards the left. Okay, and let's try to look at this a little bit further. Okay, so if the two are the same, then if Q and K are the same, then we're at equilibrium, right? The system is at equilibrium, okay? But if we're going through and if Q is less than K, okay, so that tells you that you have too much reactant, right? So then that means we need to make more product and the reaction will shift towards the right. If Q is greater than K, right? Because if we remember, our values for these are always products over reactants. So if our value is for Q is significantly bigger, that tells you that you have a lot more product than we should. So to get to equilibrium, we need to shift the reaction to the left to make more reactant. Okay, so we're going to see by comparing these values, we can determine whether the system is at equilibrium. Okay, and we're going to work through a sample problem to try to get a little bit more comfortable with this. So for calculating Q, we always need to have our balanced equation, keeping in mind the states. Remember, it's only gas and aqueous that are going in. We don't include solids or liquids. Okay, we need to know the molar concentrations at a specific time. Okay, and to calculate our value for Q, we write out our expression for our reaction quotient, just like we did for the equilibrium constant. We have to know what our molar concentrations are, and then just plug it in. So let's look at this problem here. So this is going back to the Haber process that we've seen throughout this unit. So we have N2 reacting with H2 to yield NH3. Okay, and we have 3 different experiments that were done. Okay, and we have these concentrations of reactants and products at this time point, at this time point, and this time point. And what we're asked for is, for each of the following concentrations, determine if we're at equilibrium. And if not, predict the direction that the system needs to shift to reach equilibrium. Okay, so in here, we know our value for K. We're told that in the question. We know our concentrations here. Okay, we're trying to solve for Q. We have our balanced equation. We can write out our expression for Q, which is going to be products over reactants raised to the coefficients. So that's NH3 squared over N2 to the 1 and H2 cubed. Okay, and then from there, we just need to plug in our values and compare it to our value for K. So if we look at the first scenario, if we plug in our values, so you can see we're just introducing the numbers that we got, we get Q is equal to 1.25 times 10 to the 7. Our value for K is 6.01 times 10 to the negative 2. So in here, Q is much bigger than K. So our system is not at equilibrium because they're not the same. So we have more product than we should. So the system must shift to the left to reach equilibrium. If we look at condition B, we get a value of Q as 6.01 times 10 to the negative 2, which happens to match our value for K. So we are at equilibrium. If we look at C, we get a value of 2 times 10 to the negative 3. This value is less than our value for K. So we're not at equilibrium. We have more reactants. So to reach equilibrium, we must shift towards our products, so towards the right.